All right, Chapter 5, Problem 22. We have a 0.56 kilogram squirrel with a surface area of 930 square centimeters falls from a 5-meter tree to the ground. Estimate its terminal velocity. All right, so clearly we need to calculate the drag force, which is 1/2 the coefficient, all right, the drag coefficient times the density of the fluid, which is air, times the area, all right, times the area times the velocity squared. All right, so what do we know? They say use the drag coefficient of a horizontal skydiver. That's 1, right? Density of air is 1.21 kilograms per cubic meter, right? 1. Okay, the area. The area we need to convert units. We got 930 square centimeters, right? So we need to convert square centimeters to meters. So a meter per 100 centimeters squared gets us to square meters over square centimeters. So 930 meters squared, right, times 1 over 100 squared is going to be the conversion factor. So 10 to the minus 2, 10 to the minus 4, 1, 2, 3, 4, okay, is 0.093 meters squared. All right, so 10 is 10 to the 2, 100 is 10 to the 2, squared is 10 to the 4, so 930 divided by 10 to the 4, move the decimal place 4 places over, 0.093 square meters is the area. Now, this is a 0.56 kilogram squirrel, right? So we've reached terminal velocity when your drag force, all right, drag force equals your weight, Rmg, which in this case, so we're looking for all of this up here, 1/2 c rho a v squared to equal mg. All right, so what is mg? We have a mass of 0.56 kilograms, and we have g equals 9.8 meters per second squared, right? So the only unknown here now is v squared, right? So we've got 1/2 c rho a v squared equals mg, the other g, the one that looks like a g, right? And now if we solve for v squared is 2mg divided by c rho a, and v is the square root of 2mg divided by c rho a equals square root of, okay, we have 2 times 9.8 meters per second squared times the mass is what was the mass? 0.56 kilograms, right? You know, another set of parentheses out here, divided by c, which is 1, rho, which is 1.21 kilograms per meter cubed, and then a, which is 0.093 meters squared. Okay, let's see if we can actually calculate all that without making any serious mistakes. So I'm going to just start by calculating the numerator. 2 times 9.8 times 0.56. And then the denominator, 1 times 1.21 times 0.093. I'm going to just then take the square root of the ratio. So 9.88. Okay. 9.88. It should be meters per second, right? Per second. So let's look in here. We got a meter per second squared. In the denominator, the kilograms cancel out. In the denominator, a meter squared over meter cubed. So we get a 1 over meter. That gives us a meter squared over a second squared. Take the square root, we get a meters per second. The units all work out. So terminal velocity for the squirrel, 9.88 meters per second. All right, part B. What if this was a person, right? Falling out of the tree with no drag, right? So this is just the we dropped the ball problem, all right? And so we're looking for what is their terminal, what is the velocity when they hit the ground, all right? So we know y equals 1/2 a t squared, gives us the amount of time plus the initial position y naught, right? V naught in this case is 0 because you start from rest. The y when you hit the ground is 0. So we're looking for when does 4.9. I'm skipping some steps because we've done this problem several times at this point. All right, 4.9 meters per second squared, t squared equals 5 meters. That's where we start, right? We're up 5 meters. Yep, we're up 5 meters in the tree. And so this means we're looking for when does t squared equals 5 over 4.9. The other 5. 5 over 4.9, right? Second squared, or t equals 5 divided by 4.9. Square root of 5 divided by 4.9. 1.01. 1.01 seconds. T equals 1.01 seconds. Now, if we look at velocity, v, y, equals at, and there is no initial velocity, so that second term is 0. Vy equals at equals minus 9.8 meters per second squared times this time, 1.01 seconds, right? 1.01, so 9.8 times 1.01, so we get a velocity here then of roughly the same, 9.9 meters per second. All right. Okay, that's it for that problem.